morning, dear students. We are on the CEC-UGC lecture and we are in the series of electronic circuit. We are discussing the various components of electronic circuit. Today we will discuss the one of the important gadget, which is the resonators. Resonators are of many types. In the last lecture we have discussed the electrochemical resonators, and their other type are the mechanical resonator, optical resonator, and so on. But today we will discuss the optical resonators. What is this optical resonator? Basically it is having a optical cavity, and resonating cavity or optical resonator basically is the arrangement of the mirrors or other optical elements that confines light waves, similar to how a cavity resonators confines microwaves. These resonators are used in the lasers as a major component, and as you know that we use the optical cavity or the optical resonator in the lasers to get the high gain through the medium, and it provides the feedback to the laser light. So optical resonator basically is the arrangement of the mirrors or other optical elements that confines light waves, similar to how a cavity resonator confines the microwaves. They are also used in the optical parametric oscillators and some interferometers. Light confined in the cavity reflects multiple times. Here just you know that in the laser we use the laser cavity. It may be open or it may be closed cavity, and the light is confined in this cavity. In a multiple times reflections takes place, and it produces the modes with a certain resonance frequency. It means through resonator we can get the certain resonance frequency through the multiple reflection of the light. So the modes can be decomposed into the longitudinal modes that differ only in the frequency, and the transverse modes that have the different intensity patterns across the cross section of the beam. So we are in the resonator, we have the modes like longitudinal modes as well as the transverse mode. In the longitudinal modes the frequency is having the different, and in the transfer mode intensity patterns are different across the section of the beam. Many types of optical cavity produced standing wave modes. So optical resonator can be broadly classified into many forms like parrot, ring, whispering, gallery mode, spherical, hemispherical, photonic crystals, and distributed feedback resonator. As you are seeing on the screen, there are the various type of optical resonator: parrot ring, whispering gallery mode, spherical, hemispherical, photonic crystal, and distributed feedback, that is a DFB resonator, and they are crucial for amplifying and maintaining laser light by creating the feedback loops that cause light to bounce back and forth, that will enhance the intensity of the light. Means we are getting the intensity of light, we can enhance the intensity of light through the resonator as the light is moving and bounce back inside the placement of the mirrors, which is partially reflected or the fully reflected. One side we have a partially reflected and other side we have a fully reflected, and the light is moving in this, and we can get the feedback through this loop, and that feedback will amplify the light. So different resonators types are distinguished by the focal lengths of the two mirrors and the distance between them. As resonator having the cavity, and that cavity having the two mirrors, one on the other side, then on the basis of that we can distinguish the various type of resonator. Flat mirrors are not often used because of the difficulty of the alignment them to the needed precision. So curved mirror we will use in the resonators in the optical resonators. So, the geometry resonator types must be chosen so that the beam remains stable. That is, the size of the beam does not continually grow with the multiple reflection. The size will be the same of the beam, means the beam moving in the spherical phase must be having the same. Resonator types are also designed to meet other criteria, such as we are having the minimum beam waist or having the no focal point. So, therefore, we can increase the intensity. There will be no loss of the intensity inside the cavity. Optical cavities are designed to have a large Q factor. What is this Q factor? Which is meaning undergoes many oscillation cycles with the little attenuation. Where in this regime we are just using the high Q value, that this is equivalent to the frequency line width being small compared to the resonant frequency of the cavity. So, in the optical resonator, a resonator optical cavity or a optical resonator, it is arrangement of optical component which allows a beam of light to circulate in a closed path. As we are having a mirrors, so we are saying it as a closed path because the light is moving in these closed arrangement of the mirrors. So, as the interference of the light contributes from the different round trips is a sensitive to the difference in the optical phases. That circulation leads to the resonance phenomena as it is moving inside the cavity, and which is some cases are very strong. So, in some cases light is injected into the resonator from the outside, and in other cases like in laser resonator, it is generated inside and may be partially coupled out at the some output coupler. So, what are the modes of the resonator? Now, we define the resonator modes. Light confined in a resonator will reflect multiple times from the mirrors, and due to the effect of interference, only certain patterns and the frequency of the radiation will be sustained by the resonator, with the others being suppressed by the destructive interference. Means we are taking only the constructive interference and that will be used. So, in general, radiation patterns which are reproduced on every round trip of the light through the resonator are the most stable. So, these are known as the mode of the resonator. So, what is the mode of resonator? Radiation pattern which are reproduced on every round trip of the light through the resonator are the most stable, and these type of these are called the modes of the resonator. So, they are the two types of the modes, longitudinal mode as well as the transverse mode. If we talk about the longitudinal modes, which different in the frequency from each other, and the transverse mode which may differ in both the frequency and the intensity pattern of the light. And basic or the fundamental transverse mode of the resonator is a Gaussian beam. So, resonator will work on the two modes, and essentially these modes self-consistent field distribution of the light more precisely. Electric field distributions which are self-reproducing apart from the possible loss of the power in which in each resonator round trip. So, resonator modes are essentially self-consistent field distribution of the light. And the property of the resonator mode depend very much on the various detail. Number one is the waveguide resonator. In a waveguide resonator, the transverse mode structure is determined by the waveguide properties only. As the name suggests, waveguide resonator in which the transverse mode structure is totally determined by the waveguide properties and is constant everywhere in the resonator. Once it is fixed, then it will be the same throughout the resonator. Now, if the waveguide properties are constant, only a single, then it will be constant in everywhere in the resonator if the waveguide properties are constant. Only a single transverse mode shape may exist. So, if single mode fibers are used, then we are having the single transverse mode shape. So, because of the single mode fibers. Next type of mode is the bulk optical resonator. We are having the properties depend on the overall optical setup and differ very much between the stable and unstable resonator. For stable resonator, the transverse mode pattern can be described with the Hermite-Gaussian function. The lowest order mode, that is the axial or fundamental mode, has a simplest profile, more complicated shape corresponding to the higher order mode. So, these are defined by the mode properties can be calculating using an ABCD matrix algorithm. Unstable resonator exhibit a much more complicated mode structures. Means unstable resonator exhibit means where is the frequencies are not set fixed, then it is more complicated, having the more complicated mode structure. So, which can be calculated only with the numerical means. Generally, the transverse mode size varies along the resonator axis. In each the transverse mode pattern, there are only the certain optical frequency for which the optical phase is self-consistently reproduced after each round trip. That is, in the that the round trip phases shift in an integral multiple of 2. So, in the certain optical frequency, it is a self-consistent, and these are called the mode frequencies or the resonance frequencies, and are approximately equidistant because these frequency are as it is in the resonance, so it is of the approximately the equidistance frequency we have, but not exactly equidistant due to the chronic dispersion. So, the frequency spacing of the resonator mode, also called the free spectral range, that is FSR, and inverse round trip time, and more precisely the inverse round trip group delay. This implies that the FSR becomes smaller as the resonator length is increased. So, ratio of the frequency spacing to the width of the resonance, that is the resonator bandwidth. How we define the resonator bandwidth? It is the ratio of the frequency spacing to the width of the resonance frequency that we are having, and it is called the resonator bandwidth, and is determined by the power losses per resonator round trip. So, a related measure is the Q factor, which is the ratio of the resonance frequency and the bandwidth. Means we are just calculate the Q factor for getting the gain. So, this Q factor is the ratio of the resonance frequency and the bandwidth. Now, here we are having a various type of the arrangement. So, here on the screen we are having the types of two mirror optical cavity with mirrors of the various curvatures, and showing the radiation pattern inside each cavity, and it depends upon the mirrors which we are using. Now, you see the first figure, here we are having a R1 and R2, reflection is infinity, and the plane parallel mirror length is L. So, you see that the it is a plain parallel structure. Now next one is the R1 is equal to L by 2 and R2 is L by 2. There is a fixed, length is fixed. So you see here it is a concentric spheric, concentric, or you can say having this, it is basically dependent upon the arrangement of the mirrors. Next you see that R1 is equal to L and it is confocal and R2 is equal to L. Next is hemispherical, that is R1 is equal to N and R2 is equal to infinite. Next is the concave convex. Now you see R1 greater than L1, R2 is equal to L1 minus R2. So on the basis of the mirror arrangement, we can have the various type of the resonance frequencies inside it, and depends on the reflection and the length of the cavity. So for a resonator with the two mirrors with the radii of the curvature R1 and R2, there are a number of the common cavity configuration. As you see, R1 is equal to N, R2 is equal to L. So there are the various radii of the curvature of the mirrors, and there are the number of the common cavity configuration. If the two radii are equal to the half of the cavity length, that is R1 is equal to R2 is equal to L by 2. L by 2 is a half of the cavity length. So as the length is L, cavity length is L, but here we are taking the half of the cavity length, a concentric or a spherical resonator result. You see here, this is the half of the length in the reflection, that is R1 is equal to L by 2, R2 is equal to L by 2. So this is we define here. So a concentric or the spherical resonator when we are taking the half of the cavity length in the reflection, and this type of cavity produces a diffraction limited beam waist in the center of the cavity with the large beam diameters at the mirror filling the whole mirror aperture. Similar to this is the hemispherical cavity with one plane mirror and one mirror of the radius equal to the cavity length. So in this manner we can get like the common and the important design of the confocal resonator. As we have seen, the mirror equal radii to the cavity length, R1 R2 is equal to L. So the design produces the smallest possible beam diameter at the cavity mirror for a given cavity length and is often used in the laser where the purity of the transverse mode pattern is important. And in the last one we have seen that concave and convex cavity has one convex mirror with the negative radii of the curvature. This design produces no intracavity focus of the mirror and is thus useful in very high power lasers, confocal and convex, concave and convex lens are used in the high power laser where the intensity of the light might be damaging to the intracavity medium it brought to the focuses. So less common resonator type includes the optical ring resonator and the whispering gallery mode resonator, in which the resonance is formed by the wave moving in the closed loop rather than the reflecting between the two mirrors. So it is telling about the mode, that how these the movement of the beam inside the cavity. Here we can have the closed loop, rather it is reflected between the two mirrors. So how we can enhance the resonance. So another topic is the resonant enhancement. We can take it as an example. If an end mirror is partially transparent, light can be fed into the resonator from the outside. As it is a transparent, so the light is fed through the outside. So the highest internal optical power can be achieved when the input light has a frequency matching that of the one of the mode and the spatial shape are matched. So it is called the mode matching, and as we are taking the highest internal optical power, that is the maximum transmission through a resonator, as the light we are achieved must be the monochromatic. So if we enhance, then we just require the matching. So particularly for the low loss resonators, the circulating intracavity power can then greatly exceed the input power by means of resonant enhancement, and it is called the resonant, and it is also the enhancement cavity with the high reflectivity mirror and the little additional propagation losses. Means if we get the enhancement, more enhancement, so that we have to take the good arrangement of the mirrors, as well as the resonant enhancement is also possible for a regular train of light pulses when the optical frequency of the pulse train forming a frequency comb match the optical resonances. Optical resonance is also possible for the regular train of the light pulses when the optical frequency of the pulse train match the optical resonance. In the time domain, this means that the pulse period matches the resonator round trip in between the cavity or an integral fraction of it. So what we take? We have to take the round trip of the beam inside the cavity just to get the matching with the regular train of the light pulse. So this is a and it will just make the less loss of the light inside the cavity. What is the principle of optical resonator? We will discuss that what is the fundamental principle underlying optical resonator is a resonance, and this only totally depends upon the resonance. So it is a phenomena where the light waves interact constructively within a confined space, leading to an amplification of the light intensity. That is the principle of the optical resonator. To better understand the concept, let's explore the key elements involving in the optical resonator operation. That is the first is the light wave and interference. As we are taking the constructive interference, so and others destructive, we have to leave it. So first principle in which we can get the constructive interference. So light waves and interference, light waves can undergo the constructive or destructive interference when they overlap. In the constructive interference, the waves combine in the phase, resulting in the large amplitude, while in the destructive interference, out of the phase wave cancel each other out. And in the optical resonators are designed to maximize the constructive interference and ensuring that only the specific wavelength build up inside the cavity. So this is the one of the point. So we take the constructive. So in the optical resonator, we design such that so that maximum constructive interference we can take in it. What is the role of the mirrors in the optical resonator? Mirrors is a basic point is a mirror, because here the reflection and the bounce back of the light takes place. So mirrors forms the basis of the most optical resonator by reflecting light waves back and forth within a cavity. Highly reflecting mirrors help minimize losses, thereby allowing light of particular wavelength to the resonate. So mirrors must have like that the high reflectivity we can get through the mirrors and minimum losses through the mirrors. So allowing light of the particular wavelength of the resonate. So spacing and alignment of the mirrors determine which wavelength can form standing waves within the resonator. We require the standing in within the resonator, so alignment and the spacing of the mirrors usually done accordingly as the just to get the high reflection and the higher output. Another point is the formation of the standing waves. As we put the mirrors arrangement in such a manner so that we can get the standing waves. So, when the light waves are confined within a resonator and undergo the constructive interference, they form a stable pattern, and that stable pattern is known as the standing wave. So, these waves have stationary nodes and the antinodes. So, we have the in the standing pattern, we have the two nodes and antinodes, which corresponding to the points of minimum and maximum intensity respectively. So, the formation of the standing waves in a resonator is crucial for achieving the resonance and amplification of the specific wavelength. Next is the resonant frequency and the modes. This is the most important point in the principle of the optical resonator. Because we can get, because through this resonator just we want a resonant frequency and in a particular mode. So, optical resonators support the multiple resonant frequency, and that is called as the modes. So, these modes corresponding to the different wavelength that can form standing waves within the cavity. Means we can have the multiple resonance frequency in a one resonator. So, the mode structure depends on the resonator's geometry, mirror properties and the cavity length. So, in many applications, it is desirable to operate the resonator in a single mode to achieve precise control over the output wavelength. Means by doing this, we can control the output of the wavelength through the cavity. So, it is desired to operate the resonator in a single mode to achieve the precise control over the output frequency. There are the another point which we will discuss in the next lecture with the continuation of the optical resonators. Thank you very much.